Great. Thanks for the invitation. It's always great to get to see everyone in Montreal. So maybe sometime in the future I'll come. But so everything I'm going to talk about today is joint with Juanita Pinzon-Caicedo at Notre Dame and Raphael Zentner at Regensburg. And it's really going to be a talk about basically about representations of the fundamental groups of three manifolds. So I'll try to motivate why we might be interested in that a little bit. And then I'll get into the statement of the result, and then I'll try to tell you a little bit about the proof. So I'll start with a little bit of background. And I'll try to monitor the chat, and also please feel free to just unmute yourself or ask questions. So I'll just start with sort of Perelman's, part of Perelman's Fields metal declining result, which is that suppose I have a three manifold, I'll call it Y, and let's say for simplicity that it's closed, and suppose it's simply connected, then Perelman's proof of the 3D Poincare conjecture tells us that Y is homeomorphic or diffeomorphic to S3. So that's fantastic. So now you have a way of basically certifying whether or not your three manifold is S3. You just check if pi1 is non-trivial. And sort of one of the questions you could ask, given this, sort of in a practical sense, is how do you tell if your three manifold has non-trivial fundamental group? And so maybe I'll ask that in a sort of more quantitative way, which is like, how can we measure pi1 being non-zero? Sorry, maybe I'll put the quotes around measure. So what does that mean? So it maybe depends on how your manifold comes to you. How are you going to check these things? And so one thing you could think about is residual finiteness of three manifold groups, which basically says if you have a three manifold, which is not S3 or has non-trivial pi1, then you can find some non-trivial homomorphism to a finite group. So in some sense, you can measure sort of the non-triviality of your fundamental group via homomorphisms to finite groups or via finite index subgroups or something like this. I find this to kind of, I mean, it's sort of a beautiful thing, but it's kind of difficult to work with in some sense because, you know, different three manifold, different fundamental groups might need different finite quotients to sort of, you know, maybe this group has a quotient to Z mod 2 and this one has a quotient to Z mod 3. So I don't kind of know how to compare them well. So you could kind of ask for sort of some uniform measurement of how your group is non-trivial. And I'm going to phrase that in the following way. So I'm going to state a sort of well-known conjecture in three manifold groups, which is that if pi1 of Y is non-trivial, then there should exist a representation to SU2. A non-trivial representation. So here SU2 is just 2 by 2 unitary matrices with determinant 1. So in some sense, I'm asking, can we measure the non-triviality of all three manifolds other than S3 inside of one compact Lie group? That's sort of how I think of this. So if you're not used to thinking about this group, let me maybe give some examples, or I'll give one example. So let me just give a representation from Z mod n into SU2. And the way it'll work is just, I'm going to send it to something diagonal. So it's going to be it'll be a sort of reducible abelian representation. It won't be too interesting, but it's one that I like to keep in mind. So here's a representation of Z mod n to SU2. I'm just telling you what it does to every element. And of course, Z mod n, maybe it's worth pointing out that Z mod n is the fundamental group of an order n lens space. So sort of for kind of what we maybe think of as the simplest non-trivial three manifolds, we can find some homomorphism to SU2 for their fundamental group. Okay, so but that's sort of like a very special case of three manifolds. These have, you know, metrics of positive scalar curvature. So you might think that this is sort of too special to look at lens spaces. But actually what we can do is we can put this together and get a sort of broader result. So if the first homology of our three-manifold is not zero, then what we can do is we could build a homomorphism as follows, which is abelianized pi1, surject to some finite cyclic factor, and then apply this rho n homomorphism. And so this will be non-trivial. So there are lots of three-manifolds that have non-trivial first homology. So for instance, take any surface times a circle. And so what we'll get then is, well, we'll get lots of different examples of three-manifolds satisfying this conjecture. And in some sense, if we are interested in this conjecture, we've now reduced the problem to integer homology three spheres. So the conjecture is now, I'll just rephrase it because this is what we'll think about throughout the talk, is that if I have a three-manifold, let's say a closed three-manifold with first homology trivial, and y, again, not equal to S3, so it's not simply connected, then there exists some non-trivial representation to SU2. So this is really the question that I'd like to discuss for the rest of the talk, or the conjecture. Are there any questions about this so far? Maybe I'll leave it as an exercise to think about what happens if the three-manifold is compact with boundary, or if it's non-orientable. In that case, you kind of get these things for free as well. So it's really about integer homology three spheres, whether they have SU2 representations of their fundamental group. Or if you're a gauge theorist or a differential geometer, you might want to think, do I have non-trivial flat SU2 connections on some bundle on my three-manifold? Okay, so maybe I'll tell you in what cases this conjecture is known for. It's sort of already known for quite a large number of families of three-manifolds. So maybe I'll say this is known for things like branched covers, branched double covers of knots in S3. This requires sort of deep work of Kernheimer and Rifka on instance on gauge theory. But so every branch double cover of a knot in S3, if it's a homology sphere that's not the three sphere, then there exists some non-trivial SU2 representation. Any ciphered fibered space. This is due to work of Fintischel and Stern. So ciphered fibered spaces are just three manifolds with S1 actions. I'll say any three manifold obtained by Dane surgery on a knot in S3. So remove a tubular neighborhood of a knot and reglue it. And if you don't get S3 back, then pi1 will have a non-trivial SU2 representation. And maybe I'll say one more for the symplectic topologists, which is that if you're a three-manifold bounding a nice symplectic four-manifold, then you also admit an SU2 representation. So a three-manifold, I'll say bounding, I'll say a Stein domain, or a Stein filling with B2 plus greater than 0. So sort of the rough statement is if you're a three-manifold that bounds a suitably nice symplectic four-manifold, then you can actually use the information from that symplectic four-manifold to construct a non-trivial representation to SU2. And again, that passes through gauge theory. Okay, so that's sort of what's known, or actually there's a lot more known, but these are some nice families to keep in mind for what's known. But I want to take more of a maybe sort of geometrization type approach to this problem. So I'll just remind you what the geometrization theorem of Perelman and Thurston tells us about three manifolds. And then we'll kind of take that perspective on thinking about SU2 representations. So Perelman's proof of Thurston's geometrization conjecture in a very, very simple way says the following. Here's a great simplification of it, which says that three manifolds are either ciphered fibered. So again, think three manifolds with a circle action. So think S3, think lens spaces, or they're hyperbolic. So they have a metric of constant negative curvature, or they're toroidal. So what does toroidal mean? So here toroidal just means there's a pi1 injective embedded torus. And so this is sort of, we have three cases, and I already stated that the ciphered fibered ones are known. Every ciphered fibered manifold other than S3 has one of these non-trivial SU2 representations. Hyperbolic manifolds are kind of interesting. We don't know too much about them. And if you think about what a hyperbolic three manifold means, well, you can think of it as being a quotient of hyperbolic three space by some group action. And so that basically means that your fundamental group sits as a subgroup of PSL2C, or those are the isometries of H3. And in fact, you can, with a little bit of work, you can make that into SL2C, but it's not SU2. And it's not clear how to go from SL2C information to SU2 information. And that's kind of an interesting problem in its own right, but I'm not really going to get into that today. What I do want to focus on for this talk is the toroidal case. And hopefully, if you're a hyperbolic geometer, you might find yourself interested now in the case of turning SL2C information into SU2 information. I think that's a really interesting problem. Okay, so with that, let me state the theorem that I'd like to tell you about today. So the theorem, and again, this is all joint work with Juanita, Pinzon-Caicedo, and Raphael Zentner. And it says that if Y is toroidal, then we can find a non-trivial SU2 representation. And what I'll add, sort of, there's a corollary of this, which is sort of if you combine everything we just said, that toroidal and ciphered fibered homology spheres have SU2 representations, and hyperbolic three manifolds, their fundamental groups can actually live inside of SL2C. Since SU2 is a subgroup of SL2C, every three manifold has a non-trivial homomorphism to SL2C, unless it's S3. So I'll state that as a corollary, which was originally proved by Zentner, is that sort of every three manifold, not S3, again, let's say closed, or at least compact, admits a non-trivial representation to SL2C. So there's sort of all kinds of questions you could ask about what does the space of representations to SL2C look like, or what does the space of representations to SU2 look like? All of these are interesting questions, but today I'm just going to focus on the existence problem for toroidal homology spheres. So basically the plan for the rest of the talk is I'll tell you a little bit about representations to SU2 just in general, and then I'll talk a little bit about how we'd approach this particular problem. Any questions about that? Okay, so let me give just a little bit of background on SU2 character varieties.
Yeah, just a question about in the hyperbolic case. So there are known example of three-dimensional hyperbolic manifold closed that have H1 equal to 0?
There are a lot, actually. Yeah, there are a lot of hyperbolic three manifolds with H1 equals to 0. Probably the easiest way to construct these, or one easy way to construct these, is to take a hyperbolic knot. So take like the figure 8 knot, sort of basically draw any generic knot, and remove a tubular neighborhood and re-glue it. And if you re-glue it in the right way, you'll produce something with H1 equals 0. There are also another good way to construct examples is to take branch double covers. Sort of a lot of branch double covers of hyperbolic knots will be hyperbolic and will have H1 of y equals 0. Great question. Any other questions? Okay, so let me say a little bit about SU2 character varieties. Right, we're just going to study the space of representations from a group into SU2. So I'll say for a group G, we're going to define R of G to be equals to rho from G to SU2. So just all the homomorphisms. And given a homomorphism from a group to SU2, what you can do is you can conjugate the representation just by any element of SU2. And so I'll define chi of G to be R of G mod conjugation. And you can think of this as sort of like a functor. You can think of it as a functor basically from groups to sets or topological spaces. And the way that works is that it's contravariant. So if I have a group homomorphism, I get a pullback map between these character varieties, these chi of G. So I get a map from chi of H back to chi of G. And it just works by precomposition. So I take a row and I precompose by my homomorphism. Okay. So that's the general construction. And let me give a couple examples to sort of show what these things can look like. And we'll kind of see how they might get a little bit of topology built into them. So for the first example, I'll just take, we'll just look at the representations of Z. We'll start with R and then we'll do chi. So just the representations of Z, well, Z is a free group on one generator, so I can just send it anywhere. So all the representations for Z just give me the group SU2, right? I can pick a homomorphism by just specifying where the generator goes. And then when I go to do, so when I take chi of Z, what am I doing? I'm looking at matrices in SU2 mod conjugation. So it turns out that matrices in SU2 are determined by their trace. So that's not true in general for, say, SL2C, but it is true for SU2. And so we just get all the possible trace values, which is just some interval. this is a sort of a like really key aspect to working with matrices in SU2 is that they are completely determined by their trace. Okay, great. So that's a nice simple example. Let's do a slightly more interesting example. So what I'm going to do next, and I'm not going to really justify it because we don't have too much time, but I'm going to look at the character variety for Z plus Z. So what is that? It's really pairs of commuting elements. Sort of a homomorphism from Z plus Z to SU2 should be a pair of commuting elements. And then we got to work up to conjugation. So I'll sort of just draw what this looks like and kind of highlight some parts of it. So in general, if I have some random matrix in SU2, it's sort of not going to commute with most things. It will sort of only commute with things in sort of the circle subgroup, is sort of like a circle containing that SU2, the circle subgroup containing that element of SU2. So what does this look like? So this overall, we should see a bunch of circles, but we have some central elements coming from plus or minus 1, which will commute with everything. And so what we get when we look at this character variety is actually what we call the pillowcase. It sort of has this kind of orbifold structure, these 4 orbifold points. And what do these correspond to? Here's the trivial representation. So I send the generators to +1 and +1. Similarly here, I'd send this to -1, -1. I'll let you fill in the rest. What else is going on here? On this kind of seam of the pillowcase, that's an interval. So you can think of this as, that kind of looks like the character variety for Z. And in fact, these are the representations, we'll say, which are trivial on Z plus 0. So they're really basically representations of the second Z summand, or characters for the second Z summand. And then similarly down here, these are representations which are trivial on 0 plus Z. So I'm not sort of justifying why this is the right thing. We sort of will run out of time if I explain it, but it's basically just something about linear algebra. It's really just something about linear algebra and matrices in SU2. So you can see some more interesting spaces. And I want to do one more example, which will be sort of hopefully illustrate the kinds of things we can see. So this last example, I'm going to do the character variety for a 3-manifold with torus boundary. So I'm going to look at the fundamental group of S3 minus this trefoil knot. And if you want a sort of group presentation for it, it's x squared equals y cubed. So that's the group. And I could try to look at the character variety of this thing. And the character variety kind of has an interesting structure to it. It's kind of it's kind of like a graph. It's an interval, and then another interval, and then it kind of fails to be a manifold at these points. And we have sort of the reducible representations are down here. And then the other arc, the little rainbow looking arc consists of irreducible representations. Now, sort of here's one of the key things we're going to try to do is we're going to look at this. We have these representations for the fundamental group of this knot exterior. I've removed this trefoil knot. And so what I can do is I can basically restrict those representations to what they're doing on the boundary. So the boundary of the complement of a tubular neighborhood of a knot is a torus. So what we can do is we can include the boundary of the not exterior into the not exterior. We can look at the induced map on pi1, which will actually also still be injective. And what we can do is then we can pull back. We have our pullback map on character varieties. So I'll draw that here. Remember, it's contravariant. And so what that means is we get a map from this sort of weird graph-like structure into the character variety of the boundary. So what is the boundary? Well, the boundary is a torus. So pi1 of that is z plus z. And so what we get then is we get a map from this graph into the pillowcase. So I get the pillowcase, which I'll draw here again. And so this is drawn here. And what we do now is we look at where this goes. And I'll tell you what it looks like. It's interesting. It's not an embedding, but it's sort of an immersion as far as kind of an immersion of graphs can go. So I see kind of what we saw before, but I get this double point here. So this is sort of what the, so in green, I'll draw that here. The green part, this is the image of the character variety for the trefoil exterior. So it sort of looks like an immersion in some sense of this graph into the pillowcase. And how am I identifying z plus z here, just so that you know, here I'm thinking of it as the meridian of the knot and the longitude of the knot. So in this direction, I'm doing the meridian, and in this direction, I'm doing the longitude. Are there any questions about this example? So it's something that you can, we don't have time, but it is something that you can really do by hand once you sort of understand what mu and lambda are in terms of x and y. You can really hand work out what are all the representations of the group x squared equals y cubed into SU2. It's really actually not that hard to do directly. Okay, so I hope this gives some kind of sense of what these things can kind of look like. But you might ask, oh, sort of like, how does this help? Like, okay, I've told you there are some examples we can compute and they look reasonable and we can even draw pictures of them. But now I give you an arbitrary three-manifold, which you don't know what it is. How could you possibly get any information about this character variety? And the secret is actually just Van Kampen's theorem. And I'm gonna call this the sort of intersection principle. Which is basically going to give us a way for finding representations of a three-manifold by understanding something about representations of each of the pieces when we cut it up into simple pieces. So I'm going to state it this way. Let's suppose we have two inclusions of a subgroup into a bigger group, into bigger groups. Let's say I1 and I2 go from H to G1 and G2. And let's let G be the associated amalgamated product. And we could ask for SU2 representations of G. And what's an SU2 representation of G? Well, it's a homomorphism from G to SU2. So that needs to be sort of a homomorphism from G1 to SU2, a homomorphism from G2 to SU2, And then they need to agree on the H that they have in common. And we can rephrase that in terms of these characters, which is, I'll say that we have this non-trivial representation. Basically, if and only if the images of the character varieties of G1 and G2 in the character variety for H have some intersection. So I'll write that as the pullback of chi of G1 intersects the pullback of chi of G2. This is non-empty. And where do these things live? Well, they live inside of the character variety of H. So in some sense, it's kind of now a topological problem, which is I have G, I know G1, I know G2, and I know H, and I can understand G by just looking at how G1 and G2, how their character varieties sit inside of the character variety for H. And so if H is simple enough, maybe for instance, it's Z plus Z, so the character variety is a pillowcase, then we can just look at sort of objects in the pillowcase and try to find intersections. So that's kind of where we're going to go. And in fact, what I'll do is I'm going to basically now recast this intersection principle in terms of the problem that we're originally interested in, which was toroidal integer homology spheres. So I'll kind of remind you of what we are trying to do, and then I'll try to put that into this language of sort of characters that we just discussed. So what was the setup? So we're interested in finding SU2 representations for three manifolds with H1 equals 0. So we have an integer homology sphere, and we have this pi1 injective torus. So we can draw a picture for what our three manifold looks like. M1, maybe there's two pieces, M1 and M2, and then there's this torus in the middle. And you could ask, why is this, why do I actually have this picture? Why is the torus separating in the picture? And that's because the first homology of the three manifold is trivial. So if you had a non-separating torus, then that would actually tell you that the first homology was non-trivial. So let me just point that out. There's one of the features already of working with homology spheres. So here's our three manifold, and we want to try to cook up an SU2 representation. So we want to show there exists some representation, pi1 of y to SU2, which is non-trivial. So now it's great. Now we can apply the intersection principle to M1, M2, T, and Y. That's going to be our strategy. So what does that mean when we say apply the intersection principle? Well, it means we should look at the character variety for T, the character variety for M1, character variety for M2, all of these things, and see how they relate. So I have the character variety for T, and what we're going to see is two sort of things sitting inside of the pillowcase, one coming from M1, a three manifold with torus boundary, and another one coming from M2, three manifold with torus boundary. And what we're going to hope is that those things intersect. So here we go. Okay. There might be some weird immersed objects. So here's I1 star of chi of M1. And here's I2 star of chi of M2. And what we're hoping for is an intersection point. So we hope for an intersection point. And it better be away from the trivial representation. So here's the trivial representation. And so if we find some intersection point that doesn't happen in this corner of the pillowcase, like somewhere in the middle of the pillowcase, then we've found an intersection point, and by our intersection principle, we have some representation.
Sorry, Tye, can I ask a question?
Please.
The pictures you're drawing suggest that there's some dimension features about these. Is it true that sort of the pullback of chi of M1 or chi of M1 is one-dimensional living inside this two-dimensional overfold?
The statement is basically, yeah. So I'll say it this way. So if you one way I think about this is that you're looking for flat SU2 connections. So there's some solutions to some equation called the flatness equation. And if you make some tiny perturbation to that equation, that you can still sort of get you get something which is some tiny approximation to the character variety or the image of the character variety. And that will be like a nice sort of immersed singular one manifold.
Okay.
So in general, these I think the answer is for all practical purposes, you should think of it as like an immersed graph type object inside of there.
Okay, great. Thanks.
Great. Yeah, I should stop. Are there any other questions so far for this setup?
I mean, I guess when your intersection principle, you probably don't mean non-empty, you mean sort of contain something non-trivial.
Right, so great. So yeah, like the most naive intersection principle, I guess, is just always true because you always have trivial representation. So yeah, I should say that there's a non-trivial character for G if you have these in some non-empty intersection away from the trivial representation in chi of H. Thanks. I don't know how to notate that, so I won't. But
well, it's recorded for posterity in the recording.
That's right. I've now said it, so it's required that everyone understand it forever. But I will always try to point out that we're staying away from the trivial representation. So even if it's not in this sort of intersection principle notation, I will point out like that we're really building intersection points. And I'll emphasize this away from the trivial representation.
I guess another just question based on the topology, M1 and M2 are always going to have H1Z. So you're always going to get one of these lines, I guess, on one of the edges of the pillowcase. Is that true for each one?
So right, exactly. So each of these things has each of these MIs has H1 equals Z. They're Z homology solid tori. And so if you look at their character varieties for some suitable choice of identification of pi1 of T with Z plus Z, then yeah, the character variety for say M1 will include the bottom seam, and the character variety for M2 will include the left seam. And so then you'll always, and that intersection point is telling you the trivial representation, which makes sense. And what we're going to try to show is that there's sort of more character variety that comes out into the middle of the pillowcase that somehow has to be there, and M2 will also have some that has to be there, and they somehow have to intersect each other because the topology is suitably sort of rich in these character varieties.
Okay, thanks.
That's where we're going. Great. This is great. Any other questions? Yeah, so maybe I should make mine look more reasonable. Like, yeah, so M1 will have some other stuff, and then it will also have this arc here, and M2 will have some other stuff, and it will also have this arc here, as Duncan points out. So you maybe expect to see something that looks a little more like this, where these things I've drawn on the bottom are coming from all the reducible representations, right? I have, as Duncan pointed out, for some homology reasons, the MIs have H1 equals Z. So then I get all these nice sort of abelian representations like we built before. And yeah, they'll sort of encompass these seams. Okay, so, and in fact, we kind of need some, yeah, we need some technical fact, which is kind of along the lines of what was just said. But we need some sort of basically just technical fact about homology that describes these manifolds M1 and M2 that are building our three-manifold. And I'll state it in this way, that there exist knots K1 and K2, sorry, K1 and K2 in integer homology spheres. I'll call them Y1 and Y2, such that the MIs are the complements of these, or the exteriors of these knots. And the way that these two things are glued together exchanges meridians and longitudes. So this is what we call a splice of knots in homology spheres. So Y is of the form M1 union M2, which we already know, but it's done in a way, the gluing is done in a way that plays nicely with the structures of the knots in these homology spheres. Okay, so this is just something that you can basically prove using Meyer-Vietoris. So, okay, great. So that's kind of the only technical thing that we need. We need this, and then we'll get to one other in a second. But in my last 5 minutes or so, I'm going to actually just prove the, I'm going to prove the theorem. Sort of sweeping one key technical thing under the rug. So we're going to do a proof, and there's going to be two cases. So the first case is, you should always start with the easy case. And the first case is that I have a representation from pi1 of y1, let's say, to SU2. So remember, my three-manifold is built out of the exteriors of knots and two other three-manifolds, which I glue together. And if one of those three-manifolds has a non-trivial SU2 representation, then I can get one for my original three-manifold using the following. So I'll say there exists a pi1 surjection. Maybe I'll call it phi. There exists a pi1 surjection, pi1 of y to pi1 of y1. And it really just comes from a degree 1 map. I take M2 and I squish it down to a solid torus. So I'll say squish M2 to a solid torus. And if you kind of keep track of how you squish it to a solid torus, that will correspond to the meridional filling of M1, so you get Y1 back. And then we can now pull back by this phi, and we get that rho composed phi goes from pi1 of y to SU2, and it will be non-trivial. So that's not very exciting. There's a purely non-topological way to prove this as well, but I won't do that for the sake of time. But basically, you can just kind of squish it down and then pull back. So then we have the more complicated case, which is that there does not exist a representation from either pi1 of yi, y1, or y2 to SU2. So there's a similar case 1 where we have a non-trivial representation for pi1 of y2, and we squish the other side. But now we assume that neither of these three manifolds, which we use to build y, has SU2 representations. And so maybe a good example to keep in mind for this is that yi might be S3, and so mi might just be the complement of a knot in S3, right? In that case, you know that you have no SU2 representations. And so then we get to the sort of key thing. So here you need the key technical proposition in this case, which tells us that in this case, each of our sort of pullbacks on the character varieties for the two three-manifolds with torus boundary we care about, they contain what I'll call an essential curve in the lambda I direction. In the pillowcase. And this happens away from the seams. So what I'll do is I'll draw the picture, and when you see the picture, then it will kind of tell you the proof. So here's the picture. So here's our pillowcase. Seams are on the side and the top and the bottom. Let's do coordinates. So here's the lambda 1 direction. Here's the mu 1 direction. Mu 1 is lambda 2. Lambda 1 is mu 2. That's how our gluing works. So our character variety, right, for say M1, we need to see something like this, and then something essential in the lambda 1 direction away from the seams. So something like that. There's a sort of essential, this is what I mean by essential curve, is it wraps all the way around. And now I do the same thing for M2. But now its reducibles look like this, and its essential direction is this way, away from the seams. Maybe I should say, rather than essential curve, maybe I'll say essential loop, so it's clear. So you go around, and if I have something essential going around this way, something essential going around this way, then they have to intersect. That's some intersection theory. So I'll just say that essentiality, I don't know if that's a word, but the essentialness of these two curves implies that there exists an intersection point. Again, away from the trivial representation because it's happening away from the seams. And so when we have this intersection point, well, by our intersection principle, that tells us that there exists some non-zero representation from pi1 of y to SU2. And that's what we wanted to prove. So basically the point is that if you have no non-trivial SU2 representations, then you look at these character varieties, and somehow you need to show that there's this essential loop. And then some basic intersection theory tells you that essential loops have to intersect. And so the hard thing, which I don't have time to talk about today, is how do you prove this proposition? And I'll say that the way that it goes basically passes through SU2 gauge theory. So basically sort of understanding the space of flat SU2 connections. And you get some information about this by looking at the instanton Floer homology of these yi's and on various surgeries on these knots in these yi's. But I think I'm out of time, so maybe let me stop there.
Okay, well, let's thank Tye. Are there any questions?
Yeah, I'll ask a question. Have you tried to push the method for toroidal manifolds whose first homology is small, like Z2?
I've thought about this, or we've thought about this a tiny bit, and I think John Baldwin is also thinking about this a little bit as well. The thing that gets to be a little bit annoying is if you change the homology of your three-manifold a little bit, then this technical fact changes. So it's no longer a splice of knots and homology spheres, and now it's maybe it could be kind of one of two things. It could be a weird gluing of knots, knot exteriors, and homology spheres.
Yeah.
Which is, again, you could kind of try to use the same information. Or you could have something like a gluing of a knot exterior in a homology sphere and a null homologous knot exterior in a homology RP3.
Right.
And what we actually use, so in this, what we do here is we use Fleur's original version of instanton homology. And there, like, that gets really hard once you leave the world of homology spheres and homology S2 times S1s. It's not like these, it's sort of not using one of these versions of instanton Fleur homology that should be isomorphic to some version of Hegardt Fleur homology. So I think kind of like the technical instanton theory is not as well adapted to that. So we didn't, I don't know, I gave up, but maybe there's something interesting to do there still.
Would I be right in saying that you would expect, say, if the first homology is Z2, maybe Z3, then if it's toroidal, you do get an irreducible SU2 rep.
I think that's true. I think one would expect that if it's, yeah, if the homology is sort of small enough where small enough kind of lines up in some suitable sense with when small surgeries have to have irreducible SU2 representations.
Right.
I would guess that it's the same. You should get some similar result. Yeah, there should be some generalization of this, which we haven't quite hit yet.
Right.
So at a very superficial level, this reminds me of the result by Jonathan Hanselman, Jake Rasmussen, and Liam Watson about toroidal homology spheres not being L spaces, because the argument seems to be very, very similar. Is there any connection here? Or?
One would like there to be. So, you know, what we were kind of hoping is that you could kind of improve this argument in some suitable sense to prove that the instanton Fleur homology of the gluing has to be non-trivial instead of just that the character variety is non-empty. But we weren't really able to get our hands on, and like we just didn't have enough information to turn this into a statement about instanton Fleur homology. Recently, John Baldwin and Stephen Sivek put out a paper using totally sort of different methods, just sort of like basically using formal properties of Fleur homology to prove that toroidal homology spheres have non-trivial instanton homology. And then in fact, they actually recover our result. But they don't use, but they don't use anything that is kind of similar to the Hanselman, Rasmussen, Watson picture, where they're looking at immersed objects in some suitable symplectic manifold. I think there are some kind of pillowcase models for computing instanton Fleur homology in some case, but we weren't able to really make use of anything here.
Thanks. If there are no further questions, then let's thank Tye again.